Good morning, everyone. Let us start the last class we have seen about the root locus, right? So what are the steps which are to be followed in root locus technique? Okay, so let me just revise you what are the steps to be followed while drawing a root locus diagram. Okay, so how to draw root locus for a given transfer function. Okay, so first of all, the other day we have seen that the root locus technique was introduced by W.R. Evans in 1948 for the analysis of control systems. The root locus technique is a powerful tool for adjusting the location of closed loop codes. Just a minute. Okay, so if you consider a transfer function which is k divided by s into s plus p1 into s plus p2, the closed loop transfer function of the system with unity feedback is given by what? So the other day we have seen the C of s by R of s is equal to C of s, G of s by 1 plus G of s into H of s if it is there, since it is a unity feedback system. So it is G of s by 1 plus G of s, right? So that is k divided. So for this transfer function which we have taken, that is equal to k divided by s into s plus p1 into s plus p2 plus k. This is an open loop gain, right? So what is it? What is a root locus? It is a path taken by the roots of characteristic equation when loop gain k is varied from 0 to infinity. Okay, then you will get a root locus or the root loci. I think I am clear. So what are the steps to be followed as we have discussed? The first step is, first of all, whenever you are given a transfer function, right, identify what is a open loop transfer function. Find out what are the open loop poles and finite zeros. How many open loop poles you have and how many finite zeros you have, right? So locate, first of all, identify them, then you locate them in the S-plane. What do you mean by S-plane? S-plane means you have y-axis to be the imaginary axis and x-axis to be the real axis. So here the point is, when we are talking about stability of the system, all the poles should lie on the left half of S-plane. Any one pole which is lying on the right half of S-plane drives the system to instability. We need to ensure that the poles should lie on the left half of S-plane. Any pole which is on the right half of S-plane will drive the system to instability. Because as I said, when you take inverse Laplace transform of a particular pole which is having a positive real part, then you will get an exponentially increasing function which you cannot control the system. So that is why you need to have all the poles on the left half of S-plane only, not on the right half of S-plane, right? I think I'm clear. So if at all, if you find any zeros and poles, they should be, if they are simple, they will automatically exist on the real axis. If they are complex, they should occur in the conjugate pairs. If they are complex, they should occur in conjugate pairs, right? I think I am clear. So if at all you have any poles, they should be represented by cross symbol. If you have any zeros, they should be represented by a small O symbol, right? So here you have n is equal to number of poles and m is equal to number of finite zeros. Okay, that is a representation. That is the first step. The first step is you locate the number of poles and zeros on real axis. I think I am clear. Next one. Coming to step 2, I'll give you an example. In the next coming slides, we'll try to solve a problem. Try to listen carefully, right? Don't disturb anyone. Try to listen carefully. I am trying to give you an example, 2 examples today, so that you'll understand. And I request everyone to draw this in a graph sheet after all the explain. I'll share the PPT. I'll just explain how you have to represent a root locus or a root loci in a graph sheet. Okay, if at all you are given a transfer function. So what is the first step? You need to locate the open loop poles and zeros. Second step is you identify whether you have any root locus on the real axis. Okay, as I said, you have y-axis to be the imaginary axis and x-axis to be the real axis, right? So identify whether you have any root locus on the real axis. How can you find out this? As I said, you need to take a test point. Okay, so how you take the test point? That I'll explain you in the problem, which you are going to see in the next slides. So second step is you need to identify whether you have a root locus on the real axis. Third thing is, okay, what is the third step? Angle of asymptotes. So what do you mean by angle of asymptotes? Okay, so asymptotes are the root locus branches which are tending to infinity. They'll go to infinity, right? So here, angle of asymptotes will exist. Okay, so how can you describe them? If n is the number of poles, okay, if n is the number of poles and m is the number of finite zeros, then n minus n root locus branches will terminate at 0 at infinity. Okay, these n minus root locus branches will go along as asymptotic path and meets the asymptotes at infinity. That's what I am telling. They'll meet it. they'll be meeting at infinity. That we can't see that. Hence, number of asymptotes is equal to number of root locus branches going to infinity. So, how many root locus branches are going to infinity? The number of asymptotes will be equal to that. Okay. So, this is the formula for angle of asymptotes. This is plus or minus 180. This is an odd multiple into 2q plus 1 by n minus 1, where q is equal to 0, 1, 2, 3, and so on, n minus m. Okay. And you need to find out what is the meeting point of this angle of asymptotes. That is called centroid, which is sum of poles minus sum of zeros divided by n minus m. I think I am clear. Okay, it's coming to breakaway and break-in points. Okay, so breakaway and break-in points. When they exist, breakaway and break-in points will be, you need to find out whether they are, if you have 2 poles, there will be a breakaway point. If you have 2 zeros, there will be a break-in point. Okay, if you have any root locus branch in between a pole and a zero, breakaway or break-in point may exist or may not. Find out. Okay, fine. I think I am clear. Next, so how to find out this breakaway and break-in point? You need to find out the closed loop transfer function. So after finding out the closed loop transfer function, okay, after finding out the closed loop transfer function, you need to find out the k value. After finding out k value, okay, you need to equate it to, you need to differentiate with that with respect to ds and equate it to 0. Okay, so after differentiating it with respect to 0, you need to find out what are the roots of it. After finding out roots of it, you need to substitute that roots in the k value and observe whether you are getting the k value to be positive and real. If it is a positive and real value, then that particular root may be the break-in or breakaway point that we'll see. Okay, now coming to fifth step, angle of departure and angle of arrival. If you have any complex poles, then you have angle of departure given by this formula as I explained in the last class. Okay, next, if you have any complex zero, you have angle of arrival, right? So I think I am clear. Coming to sixth step, point of intersection of the root locus, imaginary axis. Okay, point of intersection of the root locus with imaginary axis. This can be found by two methods, either trial and error approach or by Routh-Harwich method. So we'll be seeing that trial and error method here. Coming to 7 point, test points and root locus. Okay, test points and root locus. Sorry. Next, coming to the, yes, I want everyone to hear this. So you have a problem here. Okay, that is it's given by this. Wait a minute. Okay, so what is here? Sketch the root locus for the system shown in the figure. So what is that you are able to observe here? There are two gains here, which is shown by k into s plus 2. Okay, s plus 3 by s into s plus 1. S plus 3 by s into s plus 1. Okay, so what you need to do? You need to find out what is, first of all, open loop transfer function. Okay, first of all, find out open loop transfer function. I think everyone is noting down this. Okay, find out the open loop transfer function. What do you mean by open loop transfer function? Here these two are in cascade. So you need to multiply these two so that you will get k into s plus 2 into s plus 3 by s into s plus 1. Okay, so after finding out the open loop transfer function, identify how many poles and zeros you have. These are, so whenever you find the open loop transfer function, these denominator roots will be the open loop zeros and these will be the sorry, open loop poles. Denominator roots are open loop poles and numerator roots are open loop zeros. So that's what I have written here. Two poles exist at s is equal to 0 and s is equal to -1, and two zeros exist at -2 and -3. I think I am clear up to here. First of all, so I am with the first step which I have explained in the PPT which I have shown in the last class, and now also I have revised. First step is you need to identify the open loop poles and zeros. Yes, I have identified. How many open loop poles you have? Two open loop poles. How many open loop zeros you have? Two open loop zeros. I think I am clear. Okay, next. Coming to the next step. Okay. Coming to the next step. If you observe, find root locus on real axis. Okay. So in the just now I have said that how to find out root locus on real axis. Let us see this in the example. Okay, I think I am clear. I think everyone is listening to me. Please do listen. Yes, see here. Yes, okay, so find root locus on real axis. So I have represented two poles and two zeros on the real axis. So if you observe, this is the j omega axis, where this is a positive imaginary axis and negative imaginary axis. This is negative real axis and this is positive real axis. So what is that I have drawn here? If you observe, two poles are existing. One pole at origin, another pole at s is equal to -1. One zero at -2, another 0 at -3. Okay, so what is the first point? Assume a test point between two poles. So in between these two poles, you assume any test point, either here or here or here or here, whatever it may be. I have assumed here. Assume the test point, first test point. Okay, so after assuming the first test point, you count how many number of poles and zeros to the right of the test point. I think I am clear. Okay, you count how many number of poles and zeros to the right of this test point. How many poles are there? Poles and zeros, only one pole is existing. That should be always an odd number. That should be always an odd number. So since I have an odd number here, it represents that there is a root locus which is existing between these two. I have bolded it. If you observe, I have bolded it with a pink glitter. That means there is a root locus branch which is existing between these two poles. That is the point. I think I am clear. Next, coming to this one, okay, that is about the first point. What is that I have written here? Assume a test point between two poles. To the right of the test point, only one pole exists, which is an odd number. So root locus exists between these two poles. Right? Next, coming to second test point. Okay. Okay. Coming to second test point. So I have a test point here. I just assumed here. You can assume just after this pole, you can assume here, you can assume here, you can assume here. In between these two, wherever point you want to test, you can take that point. I think I am clear. So I have assumed this point. Okay. So after assuming this point, you count how many number of poles and zeros. That means total number. You need to take the sum. How many total number of poles and zeros are there here? Only I have poles here, that two in number. To the right of this test point, to the right of this test point, I have only two poles. 2 which is an even number. So what is the meaning? The meaning here is there is no root locus branch which is existing between this pole and this zero. That is the meaning. So that is what I have written here. Assume second test point between pole and zero. To the right of the test point, two poles exist, which is an even number. So no root locus exists between pole and zero. That is the point. I think I am clear. Okay. Let us shift to the third test point. So coming to the third test point, I took the third test point between these two. Either here or here or here, any point you can take between these two zeros. I took here, which is a third test point. Okay. So after taking the third test point, you count how many number of zeros and poles. So how many to the right of this test point? How many? 1, 2, 3. So which is again an odd number. Okay, 1, 2, 3. This is an odd number. Since I have an odd number here, a root locus branch will exist between these two zeros also. That is the point. Okay, I think I am clear. So a root locus branch is also existing between these 2 points. So that is how we test the root locus branches. Now you can also take another test point after this 0. You can test here and here or whatever the point you want. You can test since there are no other poles and zeros after this -3. You can test any point. So I took the test point here. After taking the point, you just observe how many poles and zeros this side. So I have 1, 2, 3, 4 poles. Sorry, 4 values. 1, 2, 3, and 4. 2 poles and 2 zeros, which is again an even number. So even number means there is no root locus branch to the left of this 0. Okay, of this real axis, which is tending to infinity, negative infinity. I think I am clear. So in the previous in the before class, I have given you an example about a pole which is existing at the origin without any poles and zeros on the real axis. Since there is only one pole, the complete negative real axis becomes the root locus branch. In the previous example, I have given you in the last class. But here, okay, since when I took the fourth test point, I have 4 as an even number, which is a total count of poles and zeros. So there is no root locus branch which is existing to the left of this 0, which is going to infinity. Okay, I think I am clear. Only 2 root locus branches are existing, that too between 2 poles here, between 2 zeros, according to the test which we have conducted, okay, to find out how many root locus branches are existing on the real axis. I think I am clear. Okay, next. So that is what I have written here in the third point to find. Okay, that is assume third test point. There are 2 poles and 1 zero. So total 3 in number, which is an odd number. So root locus exists between 2 zeros. I think I am clear. Okay, so coming to fourth point, assume fourth test point. To the right of the test point, we have total 4 poles and zeros. Okay, We have total how many? 4 poles and zeros. And that means this is a total count, which is an even number. So root locus does not exist till infinity of the negative real axis. I think I am clear with you. Okay, with the second step. Coming to the third step. Okay, coming to the third step. What is the third step? To find the angle of asymptotes and centroid. Okay, so you can test this. So what is that I have written here? The number of open loop poles and that of finite zeros are the same. So how many poles you have? You have 2 poles and 2 zeros. So what is the meaning of it is there are no asymptotes in the complex region of S-plane. Okay, that is the point here. So you can test also this with by taking the formula, which is for angle of asymptotes, which is plus or minus 180 into 2q plus 1 divided by n minus m. So what is n? N is the number of poles. M is the number of zeros. So what is n minus m value? 2 minus 2, which is equal to 0. Anyhow, you will get the angle of asymptotes to be infinity. The value, because anything by 0. Anything by anything by 0 is infinity. Anything, that means 1 plus or minus 180 into 2q plus 1 divided by n minus m value is 0 here. Okay, so anything by 0 will always be infinity. So that means angle of asymptotes are infinite. So since they are infinite, they don't exist here. That is the point. First point. Second point is if there is no question of angle of asymptotes, how come centroid you can find out? Okay, centroid is an intersection of angle of asymptotes. Okay, so there is no centroid point. There are no angle of asymptotes for this particular problem. So you can directly find out if you have total, that means if you have equal number of poles and zeros, there are no angle of asymptotes and there is no centroid question here. I think I am clear for the third step. Okay, coming to the fourth step. To find the breakaway and break-in points. So how to find out the breakaway and break-in points? What did I tell you? What did I tell you for finding out breakaway and break-in points? What did I tell you? How to find out breakaway?
Closed loop transfer function.
Yes, sir. Okay, you need to find out the closed loop transfer function. Okay, so when you find out the closed loop transfer function, sorry, wait a minute. Right. So we found the closed loop transfer function here. If you observe, so what is that? G of s divided by 1 plus g of s. So we found the closed loop transfer function like this. So that too, after finding out the closed loop transfer function, we need to concentrate on the characteristic equation here. Okay, that is the point. So I found the characteristic equation. What you have to do, that is which I have shown here, shown before, which is a of s plus k into b of s is equal to 0 in the last slide. When I am explaining the theory, a of s, okay, plus k into b of s is equal to 0, from which we can find out the k value. So you take the characteristic equation. We took the characteristic equation. I just simplified it like this. So I just simplified this one. I took the k value. So what is my k value, which is equal to minus s square minus s by s square plus 5s plus 6. You keep this aside. So after finding out k value, what you need to go with? What do you need to do? You have to find out, you have to find out what is dk by ds and equate it to 0. I took the u by v formula because I have the k value, which is a fraction. Okay, so what is the formula? V du minus u dv by v square. Okay, I simplified everything. I kept it in this formula. Okay, I found, I simplified this and I found out a quadratic equation which is in the form of 2s square plus 6s plus 3, which is equal to 0. Okay, 2s square plus 6s plus 3, which is equal to 0. Right? Fine. So after finding out, you find out the roots of these two. equations. Okay, after finding out these two values, which are minus 0.633 and S2 is equal to minus 2.366. Okay, I found out like this. You can also check with your calculator, you find out those values. After finding those S1, you substitute this S1 in K. After substituting, okay, I observed that this K value is 0.0717. So K is positive and real. Okay, since K is positive and real, this point which is minus 0.633, it may be a breakaway point or it may be a break-in point. Okay, am I clear? I think I am clear. Next. So it is shown here that, okay, let me take this out. Okay, so after taking this, okay, I got minus 0.633, which is lying between two poles, so it is a breakaway point. Okay, so wait a minute, let me show you that figure once. Okay, so here if you observe, minus 0.633 will be existing after this between 0 and minus 1, isn't it? So since it is between 0 and minus 1 and both are poles here, so that point will become a breakaway point. I think I am clear. Okay, so what is the first root I got? First root I got is minus 0.633. I substituted in K, I got it as positive and real. Second root I got it as minus 2.366. Substitute in K value, I got it as 14. Okay, so again K value is positive and real. Okay, so this can be a breakaway or break-in point. You just identify it. So after identifying that as the value to be minus 2.366, it is in between two zeros, then that point will become a break-in point. Okay, which is lying between two zeros, so it is a break-in point. Now I found the breakaway point as well as a break-in point. Okay, I think I am clear. So if you have, I have just drawn this figure here. Okay, I took j omega axis, I took 0. Okay, pole, I identified the poles, I identified the zeros. Okay, this is one of the root locus branch which is darkened by the yellow glitter, and this is another root locus branch. Okay, so what is the point here is, okay, this root locus branch coming here, okay, breaked away, sorry, okay, breaked in here, and then again breaked away like this. So this is how this root locus is existing between these two poles and these two zeros. Okay, so what is this point which is minus 1.5, which I have written here? It is the center point between this point and this point. That means breakaway point and break-in point, center point between these two, breakaway and break-in points. Okay, now coming to step 5. What is the step 5? You need to find out angle of departure and angle of arrival. So do you have any angle of arrival and angle of departure? You don't have, because our poles and zeros which we have assumed in our problem are simple.